All right, so this video is going to go over stability for nth order systems. So, an eigenvalue. For internal stability, the eigenvalues of our A matrix are the lambda i's that solve A times V vector of I is equal to lambda I times V vector of I. And this V vector I is an eigenvector. More on those later in the class. However, we know, or we're going to just say for now, that our eigenvectors cannot be equal to the zero vector, just so we can solve this equation. So we start out with that equation there. We're going to move everything to one side on the left-hand side. We're going to group the eigenvectors together. So we're going to end up with lambda I times our identity matrix minus our A matrix, all of that times our V matrix, and that's equal to 0. So if V can't be 0, well then the determinant of lambda I times our identity matrix minus A, that has to be equal to 0. And this is the formula for internal stability. It's called the characteristic equation. Now, for the characteristic equation for a linear system, it is the determinant of lambda I minus A is equal to 0. Or for input-output with transfer functions, it is the denominator is equal to 0. The characteristic equation determines stability. So for the characteristic equation, for a transfer function, it's equal to the denominator. It provides the poles to determine input-output stability, where those poles, if any of them are negative, have negative real parts, then they will be stable. In general, it's good to practice to avoid canceling out terms in the transfer function. This is more important for controls where things like pole zero cancellation can make a system seem stable, but it's actually unstable. And that's a little bit more of an advanced concept that we'll get to later. And that covers stability for nth order systems.